Hello and welcome to a new video about set theory. In this video we'll talk about some things that we can do now that we have the notion of a complement. For the most part what we're going to be doing is defining what a given operation is in terms of what it does to a set and its complement. So you can use a complement to define various operations in terms of, in different ways. All right, so first we're going to go through a couple that are very simple. First, the double complement law basically is fairly intuitive. It says that if you take the complement of a set, you just get the set, right? So this is what the complement of the set is all the members of the universal set, right? So anything that is not a member of X. And then you take anything that is not a member of the set of things that are not members of X. So basically this just means not in X. So it has to be X, right? So that's the double complement law. But then we have these complement laws, which basically allow us to define what union and intersection mean in terms of how it makes a set interact with its complement, right? So the complement law of union says that the union of a set and its complement is the universal set, right? So the union of anything that is in X and anything that is not in X, right, is everything, right? Versus the complement law of intersection, which says that the intersection of anything that is in X and everything that is not in X is nothing, right? So that tells us what union and intersection mean, right? So that's why these complement laws are nice. The next thing we're going to talk about is a new operation, which we haven't talked about in these videos yet. Remember that what union did when we looked at this as a Venn diagram, what union does is it covers everything in either of the two circles, either of the two sets is union, right? Intersection, on the other hand, just covers stuff in the middle wedge, right? So it's just the places where they're the same, right? Where they're members of both sets. What this new operation is going to do is going to capture this green area and this red area, right? So everything that is a member of X but is not a member of Y, or everything that is a member of Y but is not a member of X. And we call this operation the set difference. If you're talking about sets, you don't always have to call it the set difference, but that's what this operation is, and it's signaled because it's the difference with a minus, just like we use when we talk about the difference between numerals, which is nice and makes it easy to remember. So X minus Y, the set difference between X and Y, is all the members of X that are not also members of Y. So of these two, that would be this one, right? All the members of X that are not members of Y, right? It would be the green one. Sorry for people who are colorblind. I just realized that this is not ideal for you. What this means is that X minus Y is not the same thing as Y minus X, right? These are two different regions, right? So remember that when we were talking about union and intersection, the commutative property held for both of those, which meant that these are equal if you're doing a union or an intersection operation, right? So the union, it doesn't matter what order you put them in because you're going to fill in both circles anyway. The intersection, it doesn't matter what order you put them in because you're only going to fill in the area where they overlap anyway. With the difference, it does matter which you put first, and the one that you put first is the one you start with, and then you take out members that are also members of Y. So why are we introducing this operation now when we're talking about playing with complements? It's because probably the easiest way to define this operation is with something called the relative complement law, which you can think of as the definition of set difference if the relative complement law doesn't help that much, right? So we want to create a definition. We want to define this region in terms of union and intersection, right? So we don't actually have to have this new operation at all if we don't want it, right? This is the area that is depicted by X minus Y, right? All the members of X that are not members of Y. As it turns out, we can do this by specifying that this is the intersection of x and the complement of y. So what does this mean? So what is the complement of y in this circumstance, right? The complement of y is everything that is not y, right? So this whole region that is outside of y, anything that is not in y is the complement of y. And the intersection of x with that is anything that is in both x and in this area outside of y, which is going to give you the target region, right? So that is going to be your lovely difference between x and y. So this is why we like the complement, is because it lets us define more complicated operations in terms of just union and intersection. All right. I'm going to give, it actually becomes possible once you have the complement as a notion to define union and intersection in terms of each other. Wow, it's pretty cool, right? So this one says that the union of x and y, if you take the union of x and y and then you take the complement of the union of x and y, you get the intersection between the complement of x and the complement of y. This one says if you take the union of x or the intersection of x and y, and then you take the complement of that, it's the same thing as the union between the complement of x and y and the complement of y. I'm not going to explain exactly how these work in this video because that's going to be something that I'm going to assign you to do in your homework, because I think that now you have all these definitions, you should be able to explain that with pictures for me. These are some of the things that you can do with the notion of the complement, and I hope that you have enjoyed the video.